So welcome. Before we get started, as we do each year with the John Blume Distinguished Lecture, I'd just like to spend a few minutes before introducing the speaker just to talk a little bit about John Blume and kind of reflect on kind of his career and the things he gave to Stanford, but also as a model for all of us here. So hopefully I have a couple of minutes to read this quote that John gave actually when he participated in one of our graduation ceremonies a few years ago. John Blume was born in San Francisco just 3 years after the 1906 earthquake. And so he kind of grew up, as most people in San Francisco at that time, really with earthquakes on their mind. He went down as a young person to see the Long Beach earthquake in Santa Barbara in 1925. He was always kind of interested in that. So he came to Stanford and did his undergraduate and then an engineering degree in the 1930s. During that time, he did this engineering thesis, the Alexander Building. If you visit the Blume Center, you'll see that model there. But really working with a faculty in mechanical engineering, Lydic Jacobson. And really it was a time when I think he was bringing multidisciplinary was, between mechanical, bringing kind of rigorous structural dynamics into earthquake engineering. Maybe civil engineers at the time, weren't as well versed in dynamics as we are today. And also thinking ahead of their time in terms of nonlinear dynamics, inelastic behavior and things of that sort. Before computers were available. John graduated then and became a world-renowned firm, but then came back in 1967, or in the 60s, and completed a PhD to really kind of learn some of the, between 34 and 67, things like computers came on the scene, some of the probabilistic modeling and stuff. And really, that's got to be the epitome of lifelong learning. I don't think he stepped away from his practice, but to make time for PhD studies in the midst of running a world-class company. Just a couple of shots here. This is for the students just to show, the dress code's kind of, it's changed over the years. The old lab coats. Mike still dresses that way. Mike Dresser-Leppert. And of course it was the 1906 earthquake again that really got folks here at Stanford, across the bay at Berkeley, down at Caltech, really kind of focused on kind of earthquake engineering that's kind of stayed with us through today. John Blume and Associates, did a number of remarkable projects, kind of, structural engineering, but some leading edge projects at the time, tall buildings, worked on bringing probabilistic modeling, looking at the early work on nuclear power plants, kind of embracing a lot of the research being done here at Stanford, Professor Karamidjian and others before, working on probabilistic models coming into and I'll get to that in a second. And the linear accelerator, just interesting structures, so really things that are pushing the envelope. What amazes me too is that Blume and Associates, the alumni from that is, I don't know all of them, but it's kind of a who's who of structural engineering. When I first started my career, I had the privilege to work with Les Robertson in New York City, who was the designer of the World Trade Center and other tall buildings around the world. Well, when Les first got out of school, he worked with John Blume and Associates. Eric Elsesser, you might know the firm Farrell Elsesser up in San Francisco. He was another one that came through as a young engineer through John Blume and Associates. He saw that two big egos couldn't stay together in the same place, so he graduated these people. Sig Friedman, who's kind of another legendary, went over to West Johnny Elster, another alumni. And Marty Zarnecki, who's here with us today, stayed with John Blume, started his career with John Blume and Associates, became URS Blume. URS has since become part of AECOM. But Marty continues kind of in that tradition. So I think that the magic of John was having these ideas, but also having the charisma and bringing people in, to believe in those ideas and bringing kind of a team together. In the 1970s, he kind of gave back to Stanford in a big way by creating an endowment that funds the Blume Earthquake Engineering Center, which many of us are beneficiaries of. And these are some early pictures of when it was getting started. The two founding directors of the center, on the right there, Jim Geer and Naresh Shah, pictured with John Blume on the shake table. And then under Professor Karamidjian, might have been student Karamidjian in those days. There's, I'm not sure if you squint, you can see that sign there. It says the main computer.
32K memory.
And again, that was just, John Blume kind of, giving back to the university he loved and believing in kind of students. And really, again, trying to, research into practice, pushing that. So anyway, that's just kind of a few remarks just to reflect on that, we're all beneficiaries of the ideas and things that people that have come before us. And so just to think of someone like John, his commitment to technical excellence, curiosity, all those sort of things, and then building it into profession, and ultimately it's people. And even today, the Blume Foundation continues to support the activities in the Blume Center. So with that, I now have to introduce our distinguished speaker. And it's always kind of hard, after we've heard about John Blume, to say, well, what's so distinguished about our speaker? But it's really, our speaker is extremely distinguished. Glaucio Paulino, who's a professor at Georgia Georgia Institute of Technology, Georgia Tech, and holds the Raymond Allen Jones Chair there. He's been there about a year. Prior to that, he was at the University of Illinois, and actually prior to that at UC Davis. And you have in the brochure here a little bit about Glaucio's kind of background and many of the awards he's won and things. So I won't go through that list, but I did want to say a couple of things about his background that don't come through there. He's originally from Brazil, did his undergraduate degree and a master's degree at the University of Brasilia, and then PUC, Pacific Catholic University in Rio de Janeiro, and then came to Cornell University where he did his graduate studies. Kind of throughout all his research, he really has a passion for mechanics and computational mechanics. But I think like John Blume, he kind of took that passion and it really evolved through his career. And he's continued to kind of push the boundaries on that. I think some of his early work on computational method, boundary element methods for computational techniques in fracture and damage mechanics. And a lot of his work there, including a book he wrote, is kind of widely cited and used. Many people would carry that out through their career, but Glaucio was kind of not discontent with that. He still does that stuff, but wanted new things. So he got interested in topology optimization, and we're going to hear about that today, for structures and also different multi-scale, multi-physics problems. What I personally find most kind of remarkable of that is the rigor of the mechanics he brings to topology optimization, but also working with things that's dear to my life is design of buildings and tall buildings. Glaucio has a collaboration with Bill Baker, who's the head structural engineering partner at SOM. Bill Baker designed the Burj Khalifa, the tallest building in the world, and through collaborating with Glaucio has really kind of pioneered a lot of the topology optimization and actually putting it into practice in these tall buildings. Glaucio is also, and we'll hear some of that today, looking at structural topology optimization in other fields, biomedical and so forth. One thing we won't hear about today is some of the latest work he's been looking at on deployable foldable structures. And I think he might be on path to create what I'll call computational origami, a new field. And if you look at his website, there's kind of some fascinating examples of work he's doing there. I would mention that a recent paper he's written on that was just been awarded the Cozzarelli Prize from the Academy of Sciences. That's kind of one of their top paper prizes of the year for their journal. So quite an accomplishment. And finally, apart from those things, I think as strong as Glaucio's passion is for mechanics and all the technical topics and the research, it's an incredible commitment to kind of education, scholarship, and really kind of advancing society through the things he's working on. And I want to mention one other thing is that a few years ago he became a program director at the National Science Foundation. And the National Science Foundation is often asking faculty from top universities to please come and direct programs there, and most of us kind of duck because it's kind of perceived a little bit administrative. It's a very service-oriented role. You put a lot of time and energy into it. So again, most of us kind of sort of duck. Glaucio stepped up, went to NSF, and really energized the program he was in at the time. I mean, developing a lot of new ideas, and when you go to panel reviews with Glaucio, you came away kind of inspired and things like that. And I think to me that's one example of the way he started giving back. But I think when we think about who we invite here for the Blume Distinguished Lecture, it's both the excellence, but it's also the character of that person. So anyway, with that, I'm pleased to welcome Glaucio.
I am very happy to be here today. I have enjoyed every minute of my visit, all the meetings, and especially the meeting with the students. That was a very nice, very inspirational meeting. And when I read about John Blume, I was quite moved. And I highlighted here a few things, is that he got his degree in 1933, and as Greg indicated, at that time he already had idea to do multidisciplinary work. He created his own study plan, a mix of courses in geology, architecture, and math. And the next two items really called my attention because they also relate very well to what I wanted to show here today, that is the connection between engineering and art. John, having a wonderful musical talent, he was a second tenor in a quartet that used to sing with dance bands in the Rose Room of the Palace Hotel. And also he was a musician, and he used to play the guitar and the banjo. So he had engineering and artistic talents. He was a man of many talents. Something quite amusing is that he did his PhD after 30 years of getting the bachelor's degree. And he got the BS degree in 1933, and then he came back in 64 at the age of 55 to get his PhD, which he got in 67. And also, as Greg pointed out, he was quite a philanthropist, and he had a great dedication to Stanford with several fellowships and the endowed position that is held today by Greg. So before I go on, I also would like to thank all my students in one way or the other. This has their contributions, and also the sponsors to this research, especially NSF and SOM. And here is a brief outline of the talk. I will essentially give a brief introduction to topology optimization and additive manufacturing, talk about polygonal finite elements and how can we do a stable topology optimization calculation, how to generate those meshes, performance of those elements in elasticity and multiphysics, talk a little bit about mixed variational problems and the implications of polygonal elements with mixed variational problems, building design, the work we have done with SOM, the craniofacial reconstruction, and then the conclusion of the talk. Essentially, the goal of topology optimization is to find the most efficient shape of a physical system. Here is an example of a project that we got involved with SOM. And essentially, the key idea there was to design the bridges that would connect these towers. And the client, this was a client in China, did not want any conventional design, wanted something unique, something different. We played with our codes, and then we came up with this design that you can see here. And this indicates to you that in general, topology optimization offers an avenue to bio-inspired designs. If you look closely on this, you can see that it's similar to the shape of a spider web, not just in terms of appearance, but also in terms of properties. So now one thing that people have realized with the advent of additive manufacturing and 3D printing, and I brought a few models here to share with you later on the talk, is that topology optimization has a great connection with additive manufacturing. Today we have many techniques. I have listed a few of them here: stereolithography, selective laser sintering, color jet, FDM, direct metal printing for different types of materials, polymers, ceramics, and metals. And there are several issues, and this is quite a prolific area of research that is going on right now. And just a very brief review. For example, topology optimization is wonderful to design cellular materials. What we can see here are materials that have a negative Poisson ratio, and then a cellular material interpretation of the continuous optimization results. And the papers where these pictures were taken from are cited over there. And it's also great in the medical field, as I am going to motivate further. And it has a lot of applications, for example, in bone implants and different types of implants, and in getting materials with prescribed properties, diffusivity, stiffness, and so on. And this is an interesting one where Gaynor and collaborators, they use topology optimization to design efficient, effective, compliant mechanisms. This one was done using Vero white and Tango black. and then this allowed them to avoid hinges. That is a very common occurrence when you do the design, and allow greater deflections. So this is an application of 3D printing and the topology optimization to design compliant mechanisms. This is a very interesting one in general when we are printing, especially when we are thinking about civil engineering structures where one dimension predominates. The printers hate that. They don't like that. What does it mean? Is that if I print something like this, or let's say something like this, what happened is let's say the black here that you see is the material. If you think that this material, the volume here is V, in general, most of the time I am printing what I do not want. I am printing support material that may be 2 times V, 3 times, 4 times, it depends. But I print much more things that I do not want than what I want, especially for civil engineering structures, like where one dimension dominates over the other dimensions. And then this work is quite interesting because they have developed a technique that allow you to, for example, modify the topology so that you can print the material in a way that reduces the amount of support material or eliminates it. So now let me briefly talk about the topology optimization formulation, and I wanted to talk about it in the sense of a PDE constraint optimization framework. And here, for example, let me refer to the compliance minimization problem. This inner product here, traction with displacements, essentially this is the compliance, and I want to minimize the compliance or maximize the stiffness. And here I have a volume constraint, and this is a Lagrangian, and this is a Lagrange multiplier associated with that constraint. The more constraints I put, the more Lagrange multipliers I am going to have in the problem. And notes that essentially in topology optimization, we want to find the topology, and then here this functional will be a function of omega, of the shape, and also of the displacement field. And notes that there is an intrinsic and implicit dependence here of the displacement field on these characteristic functions, on the shape of evolution. As the shape changes, the PDE, the governing PDE is going to change. And then here are my governing equations and the boundary conditions with Dirichlet and Neumann parts of the boundary, and every time that I have a new hole, then this will be traction free. In summary, what happened is that this problem is U-poles, because in general, computationally, we cannot work in the space of those characteristic functions. Then what we do, we parameterize shapes using density functions that are continuous, and then the problem is transformed into one of a sizing optimization. And now I rewrite the previous functional in this way. And I want to call your attention again is that here in the optimization I have 2 fields, right? I always have 2 fields. One is the displacement. I am referring now to a displacement-based formulation. And the other one is the density field. I have 2 independent fields, and there is an implicit dependence of the displacements on this density field. And then the problem is reformulated in this way. And a few things here that we need to pay attention is that I rewrite the stiffness tensor in this way, because what happens is when I create a void, instead of having a void, what I am going to put there is what is called the ersatz material. Ersatz material. You can see that if you make rho equals 0 here, you get epsilon c, that's what you get there. And rho equal 1, then you get C, that is the original stiffness tensor. And then this also indicates the SIMP. The SIMP means solid isotropic material with penalization. That's the constitutive model that we are going to use, that has this penalization parameter P here, so that we can drive the design to a black and white solid and void solution. Okay. Now, I need to discretize this. I need to do finite elements, and now I would like to also ask the students here who has done FEM. Okay, many of you. But then what happened is, essentially, if we look in any book in FEM today, in general, there are only two types of elements, triangles and quads, right? Either in 2D or 3D. In 3D would be tetrahedra and bricks. Isn't that right? Did anyone study a different element? But then my question is, why not? Why couldn't we have elements, let's say, if we are in 2D polygons that would have 4, 5, 6 edges, 7, 8, 9, 10? Could that give us some advantages in the formulation? And the answer turned out to be yes, and that's what I will try to motivate to you. And these polygons, we can see them in nature, in geological geometries, botanical, zoological, and so on. And also now, coming back to the art connection and to Blume, right, there is also a novel that was written some time ago called Flatland by Edwin Abbott in the late 1800s. And this tells us about a flat land, a two-dimensional society that is populated by polygons. And the story is told by Mr. Square. That's a regular member of the community, not too many edges. And the most noble of everybody in the community was the priest that had an infinite number of edges, a perfect circle. And it's a very nice story. And then if I use the polygonal elements to do the topology optimization, I get something very interesting here. It is very well known that if I use a lower order element like a Q4, for example, or a triangular element with a constant density, and I try to find the topology of this beam, you see what I get. I get a checkerboard. I get a useless solution. Of course, you can post-process this solution. You can apply filters and so on, but I don't want to do this right now. And what happened is, if I use the polygonal element without any other treatment, it seems I get a stable solution. This means that this is unstable. With the polygonal element, I get a stable finite element solution, and not only that, I get a Michel type solution, as you can see here. Okay? So by virtue of their geometry and accuracy, these low-order polygonal discretizations, they seem to be free of those instabilities. And now I want to come back to the two-field, to the mixed variational problem. And the checkerboard can be viewed as a global instability similar to those that are encountered in a mixed variational problem, in two-field problems. And here essentially I have a statement of elasticity and optimization. And the important thing here is that when I linearize these conditions, and if I am sitting at a U0 and ρ0 and I give an increment, I can rewrite these equations in this form. And for a linear stiffness model, this system has a similar structure as that of Stokes flow in fluid mechanics. Of course, some of the spaces are different and so on, but the basic overall structure is the same. Therefore, some of the techniques that is used in mixed variational problems can also be translated and used in topology optimization. And I am going to elaborate a little bit on that. And let's see how these elements perform. For example, this is a Michel cantilever problem. Okay, this is the design domain, and there is a load here at the tip. And if I do the topology optimization, then you can see that I get this solution that resembles very much a Michel solution. In general, I have curvilinear members here, and they meet at more or less 90 degrees. Okay, the analytical solution should be around 90 degrees, and looks a nice solution. Now, I am comparing this with a higher order element, a quadratic element with a constant density, because in that case there is no checkerboard. But look what happened. It seems to me that there is another kind of instability there that is associated to the simplex geometry of the element. You get very long straight members, and then you get one node type connections here. So it doesn't seem to be as good as this one that you see on the left. We have also been working on local stress constraints. Everything that I talked to you up to now was a global optimization. But then, for example, if I want to deal with stress constraints, this is a local problem. Then I have to treat the optimization problem locally. And then what we did here was to solve this problem here. It's a very typical, very common benchmark problem in the literature with a load P there. And what happened is here we use the level set discretization, and then in the solution, if the solution works, I should round this corner here so that I would eliminate the singularity of stresses over there. And the way we treated this was by means of an augmented Lagrangian approach where we have, for example, close to 20,000 constraints. I think the local problem should be treated with local approaches. One of the approaches in the literature today is to treat the local stress constraint as a kind of a global problem with a kind of a clustering technique, but I think that can be problematic. Now let's look at these elements in a multiphysics problem, and let's think about piezoelectric materials. A piezoelectric material is a material that can convert a mechanical input into electrical and vice versa. Has anyone here been in Japan, for example, and used the Shinkansen? You have? So good. Then what happened there is that all the energy that is used for admission and also for the signs is generated by you, by the people that are using the system, because this is a piezoelectric floor. When you apply pressure, that pressure is transformed into electricity that is used here. Another idea is to do an insole, a piezoelectric insole in the tennis shoe. So if you need to make a phone call, for example, in your iPhone or Samsung, right, then you can just walk or run. It's not that much energy, maybe 10 joules per step, but then you may have enough energy to make your phone call. And also they are using this in tennis rackets today, so that actually Andre Agassi used one of those rackets in 2002. Turned out he lost the game, but he used the racket. All right, so this is a piezoelectric material. And then we have here epoxy in blue, and the yellow is the PZT, the piezoceramic, and then we fix the polarization. And the one thing that we want here is to maximize the electromechanical conversion parameter, that is kappa. So the bigger the kappa, then the more energy I can get. And then you can see again that when I use quads, it seems that I get trapped in a kind of a local minimum there, and you can see the solution has a lot of influence of the Cartesian geometry of the element. However, with the polygonal, it seems we don't get that dependence of associated with the simplex nature of the element, and we can also get a better kappa, as you can see over there. Okay. Now, how do we do the finite elements? One challenge that we have on this are the shape functions, how to get shape functions. And this is a very active line of research today. There are many types of shape functions that can be used, like a watch press, maximum entropy, harmonic, mean value, and so on. And all of them have pros and cons. Here, we use the watch press that is given, each shape function is given by this ratio, and each alpha is illustrated here. Essentially, these functions are non-negative, linear on the boundary of the polygon, and linearly complete. What is one important thing for us is that they are non-negative because we don't want our densities to be negative. And then that property can be used. Also, very nice meshes can be generated. And even on different scales, for example, we can use elements that change in size from very small element to very large, and this can be very helpful in modeling. And also in 3D, for example, there is a tremendous amount of work that is being done at Sandia National Labs on 3D meshes with polygons. And recently, because we want the community and the students to use this, then we wrote this paper on Polymesher, a general purpose mesh generator for polygonal elements written in MATLAB. And essentially, it uses level set and sign distance functions that allow you to very easily generate polygonal meshes. And also, we wrote another paper that does the finite element and the topology optimization. These two are educational papers, so that if you have a hook domain like that, you put your boundary conditions, generate the mesh, and then you can do the topology optimization and get those results. All those codes are available on my website, and in the software part, the software header. If anyone is using a computer, you can just check, and it's very easy to download, very easy to use. If you are interested and want to talk more about this, I will be glad to talk to you. And now let's talk about the next stage. Now we have been talking about finite elements, then we use shape functions, and as I said, that can be a challenge. What about if we forget about shape functions? We don't use interpolation functions anymore. This is the idea of the so-called virtual element method, that is a reincarnation of what is called the mimetic finite difference. In the mimetic method, essentially continuous differential operators such as GIF, curve, grad, trace, and so on, they are mimicked by their discrete counterparts. And the VM, or virtual element method, essentially has had a lot of work recently. The first paper was written in 2013. It's this paper here on basic principles of virtual element methods in Professor Franco Bretzi's group. And since then, there has been a tremendous amount of interest. And in a nutshell, what happened is, let's suppose that we need to calculate our bilinear form here, or in other words, we need to get our stiffness matrix. And then these methods give you two conditions. One is a consistency condition, and the other one is a stability condition that is illustrated there. But the important thing is that the consistency term will ensure that the patch test is passed, okay? And you need to satisfy the stability requirements, but at the end, you can get matrices that are like that, and you can really compute them and get your stiffness matrix. Okay? That's the stiffness matrix, your bilinear form of your formulation. Now, let's see how this works. We have observed improved accuracy for 3D elasticity problems when polyhedral discretizations are used. And you can see here that this is a random Voronoi tessellation, and this is what is called CVT, a centroidal Voronoi tessellation, and this is X regular bricks. And you can see that the CVTs are much more accurate than the other discretizations. And we recently published this work in CMAME. The reference is here. And then we applied that also to topology optimization. And the details are given in this paper here that you can find in CMAME, was published last year. Now, since we said that we can relax the requirement for interpolation functions, then we may think about elements that have different shapes. And now I want to refer to Escher. Are you familiar with this? Great, right? And a great Dutch graphic artist. And then, for example, this is from Escher's own work. And now we can think about doing a mesh, for example, that will have a Pegasus. And the way to do it is that you have this surface here, you move it there, do this one, and move it there. And then you repeat this many times, and then you have this kind of elements. Okay. And again, this, I think, reminds us of the connection between engineering and art. And then we wrote this paper here on bridging art and engineering using Escher-based virtual elements. And this allows us, for example, to do topology optimization. This is the Michel problem. And we use a bird here. And then if you see here, it's quite interesting because you can see that the birds, they fly to the topology. Right? And it's quite interesting. Why do we have to use triangles and quads? We can use other types of elements, right? So, and all the details are shown in this paper here. And now, very briefly, what I wanted to come back now is to talk about a mixed variational problem and consider the incompressible Stokes flow, the viscous flow with viscosity mu. And what I wanted to tell you essentially is that we are going to use, similarly to topology optimization, what we are going to do is to use linear polygonal elements on the boundary for the velocity field and a constant pressure. What is amazing is that, for example, anyone that works here with mixed problems is very well known that if we use, for example, a Q4 right, with a constant pressure, that is an unstable formulation. This is the pressure, it's a checkerboard, it's unstable. But look here, without any treatment, then the polygonal element is stable. You can see we don't get this checkerboard, and what we also looked was the necessary condition for stability, or the if-soup condition, the Babuska-Bretzi condition, and we checked a few discretizations, and what this says is the following. If I keep refining the mesh, do finer and finer and finer meshes, and this stabilizes, this is a necessary condition for stability, okay? But if this does not stabilize, clearly the element is unstable, and you can see here, as we know, quad is unstable, but the polygons and the hexagonal meshes, they are stable. And this is very nice. And later on, someone in Franco-Bretzi's group proved the sufficiency condition for stability. And maybe just one problem here that we know the analytical solution, this one, because this is quite interesting. What we did, again, the velocities are just here on the boundary, and is all linear on the boundary, okay? And the pressures are constant for all the polygons. And we compared the solution here with the mini element by Arnold, that the velocities are shown here and has a bubble mode, and the pressure is higher than this one, is continuous, right? And you can see here that when we look at the error in velocity and also in pressure, you can see here that the CVT is more accurate than the quads and even the mini element. And also for the pressure, the CVTs are more accurate. Now, what we decided to do was to compare our low order polygonal elements with the higher order elements that are available in the literature. For example, this one is the Borval and Peterson macro element. The velocities are circles and pressure are quads. As you can see here, is a continuous pressure. This is the Taylor-Hood element, right? A quadratic velocity field and a linear pressure, okay, continuous. And this is the Crusoe-Ravier element. And as you can see, quadratic velocity and linear pressure, like this one. However, this pressure is continuous, and the pressure here is discontinuous among elements, okay? And I will just call your attention here for the error in pressure. We were quite surprised, because if you look here, the best element is the Crusoe-Ravier. But look at the second best, is the low-order CVT, the polygonal elements. So we were quite surprised about this, and then we used these elements, we used the mixed variational formulations to do both the fluid flow calculation and the topology optimization, and this is a paper that will be published very soon in structural and multidisciplinary optimization. Now, reached the point where I want to talk about one more application here, that is the craniofacial reconstruction. All the theory, the theoretical part we finished. And here is the idea, the question, if engineering can help the medical field, and then if how we can help these cancer patients that essentially they lose a lot of bone on their face, okay, and they can have very horrible deformities, and also this can be helpful for soldiers when they go to war. They can protect their body very well, but they cannot protect the face too much, because if you protect too much, then you cannot see, you cannot smell, and many times they get tremendous injuries and deformities, okay? And here is just an illustration of the problem. Here is a patient before cancer is detected, and after the diagnosis of cancer, then you can see that there is a terrible tissue destruction, deformity, and this leads to a decreased quality of life. And you may have friends that have had cancer. You know that the treatment is very invasive, involves surgery, radiation, chemotherapy, and so on. And essentially, in order to do this, in order to help these patients, this was a collaborative work between cancer surgeon, Dr. Miller, and myself, and some of our students. And what we used here for the topology optimization is a technique that is called multi-resolution topology optimization. In general, in the literature, most elements, there's a finite element, and then you have a constant density. But here, we have different meshes. We have a coarse finite element mesh, and then we can have different discretizations for the density mesh and the design variable mesh. And then this gives us an inner resolution, a multi-resolution inside that element, okay? And recently this idea was used by the Danish group at DTU to do an app for the mobile phone that you can download. If you type TopOpt, that is the short for topology optimization, you can download this app and play with it. And they use the MTOP as the engine for the app, okay? And for example, here is a problem, craniofacial reconstruction problem, and again, this is tailored for the patient. We start with the MRI data, thousands of slices of data for a specific patient, and then from that we can build our design domain, the boundary conditions, the initial conditions, and from that point the doctor can play with different scenarios to decide which kind of implant is going to be used in that specific patient. Okay, and here is one illustration of different types of maxillectomies. Okay, and then here is another illustration, for example, of the kind of information that the doctor can get. The key idea is that the topology optimization is not going to remove the work of the doctor, but is going to help the doctor to make better informed decisions to help that patient. This work was recently published in PNAS, and recently the National Science Foundations, they did a Science Nation video about this work that I would like to share with you.
It may not be clear at first what Ohio State University plastic surgeon Michael Miller
This is what we use in the PNA.
and engineering professor Glaucio Paulino at the University of Illinois have in common. But together their research aims to help people with disfiguring facial injuries.
You can see here an example of a patient who may have lost this part of their face from either a blast injury or from a cancer.
With support from the National Science Foundation, Miller and Paulino are using technology called topological optimization to one day rebuild faces and lives.
Topology optimization is a technique that allows us to find where we should put material and where we should not. If we can use this technique to optimize buildings and cars and airplanes, why can't we use it to optimize the human being?
But bones, blood vessels, and tissues are far more complicated than mere machines.
Within this small space, there's functions of our vision, our smell, speech and swallowing. Restoring all of these functions is extremely challenging.
They use mathematical formulas to model replacement facial structures customized to each patient.
The computer is beginning to create a structure within that region. You can see it becoming more and more refined.
It will be some time before Miller will be able to use optimized replacement parts during surgery. A long-term goal is to have patients regrow their own bones.
I'm confident that the day will come when we can engineer bones to replace the types of bones that someone may lose in their face.
On the material design part.
Often sharing ideas long distance, Paulino and Miller say it's been exciting and humbling to tap into each other's talents, and they hope the rewards for patients will be long-lasting.
To restore defects in patients who've had major loss of facial tissue, bones in the face, it creates an enormous benefit for that person.
Using bioengineering to restore a face devastated by trauma. Now that's an idea worthy of a smile. For Science Nation, I'm Miles O'Brien.
Essentially, this work is being continued now, especially Dr. Miller moved to Ohio State. They are trying to include, for example, modeling of oxygen transfer in the surgical tissue and doing some experimental validation. And then this brings me to the transition slide where we found this slide here in the medical literature journal of craniomandibular practice, where they compared the human skull and the Gothic cathedral in terms of the transmission of forces. And then this essentially, right now I will summarize some of the work that we did in collaboration with SOM and address the connection of the design that we are going to do using density methods and the ground structure methods with additive manufacturing. So the key idea now is that we are going to use a ground structure method. Suppose that this is a design domain, and then you put lots of points there, and then you connect every point with every other point, and then the topology optimization is going to tell you where the optimal structure is. And this is similar to the ideas of compressed sensing. For example, if you have a photo in your iPhone, 6 megapixel picture, you don't store all that information in your iPhone. You only store 1% of that information or so. And that similar idea here, then there is a structure here, and where it is, then if you pay attention, if I separate this here, then the structure I'm looking for is right there. And the question is, the topology optimization will help us to find this structure. From all these members, and we may have thousands and thousands of members, I only need a few. These are the ones I need. Okay. All right, then we are going to use this technique that is called ground structure. There are many types of formulations. I will just concentrate in this one here called the plastic formulation. Suppose in the structure I want a minimum volume because in general that means a minimum weight, right? Subject to equilibrium, for example, and stress constraints. I don't want my stresses to be unbounded, and also I want the areas, for example, to be non-negative. Suppose that I have a discretization like that, a polygon, and let's pay attention only at this node here, okay? Well, that's what we are going to pay attention. And then if I have a level 1 connection, then I am going to go here and do truss members between this node and every other node that is connected, okay? This is a level 1. If I do a level 2, then I go to the next level, and then I will, again, I am only paying attention in this node, then I am going to connect this with all the others, all the other nodes in the next level, and so on and so forth. Is it clear? Does it make sense? Okay? So then, but now this formulation has some problems, has a vanishing constraint problem that induces some problems in the formulation and in the solution. So I want to convert this geometry and size optimization problem into a sizing only problem. And then this is the problem. And then what I am going to do now is to multiply the inequality constraints by the cross-sectional area. And now that I have this, what I am going to do is to transform those two inequalities into equalities. And a very common technique in optimization is to use slack variables, and that's what I am going to use here. The slack here are forces, okay? These S are forces. Plus means tension, minus means compression. And then at the end, the formulation will be like this. And that's the one that I am going to work with. And so the summary is that now I had only one set of design variables. Now I have twice the number of design variables. I have S plus and S minus. I doubled the number of design variables. That's not very good, but that's what happened. And however, I don't have that vanishing constraint, okay, anymore. That's very nice, and I can deal with different limits for the stress in tension and compression. And this is an LP problem, and then I can use linear programming. For example, the interior method by Karmakar, for example, I can use that to solve the problem. And if you are interested on that, there is a wonderful paper here by Margaret Wright on the interior point revolution in optimization, history, recent developments, and the lasting consequences, talking about this great idea by Karmakar. And maybe I can just say this. Before Karmakar, when he did that, he was 26 years old. And before Karmakar, the idea is that optimization, there is linear and nonlinear. Even the books, you don't mix them up. You don't mess with them. Linear is linear, nonlinear is nonlinear. Okay? And then the best method at that time in the world was the simplex method, and by George Danzig. He happens to be from Stanford. And then what happened is Karmaka had this brilliant idea to use a nonlinear optimization techniques to solve a linear problem. And in general, in this paper that he wrote, he reports his solutions that in general were in the range of 50 times faster than the simplex. So that is a very nice story. Let's come back here. Then I have a mesh, and then I can generate the ground structure. This is level 1, 2, 3, and I explain how I do these levels, and very soon it saturates, as you can see. Okay, so this is basically a full ground structure, and now I can solve the same problem either using a density-based method, as you have seen before, or the ground structure method. And now I am going to concentrate a little bit on ground structure methods. And one of the few problems that has an analytical solution is the torsion ball problem. And then we played with this problem, as you can see here. And this has an analytical solution that was provided by Michel. And we can investigate this solution in a different domain. And then we used this domain here, and we got this solution, okay, that I want to share with you. And then we also 3D printed this. We started with a few million bars in this domain, and at the end these are the only ones that we have. And I'll pass this around. This was done by means of a selective laser sintering technique. Selective laser sintering, SLS. If you put your finger here and you follow this, this is a beautiful log spiral that coincides with the Michel solution. Another point that I would like to make is that there were some questions in the literature before if we needed interior members for this solution. If our solution is correct, this shows that we don't. Okay. This is just to show that we have a convergent solution as we refine the mesh. The error decreases. And this is a study that we did with the Lotte Tower in Korea. And we use both diagrid type solutions, ground structures, and density-based methods. And here is one of the solutions that we got. Essentially, super tall buildings are like very long cantilevers, right? And what happened is that this one, because is a bending type load, then you can clearly see. You can clearly see that we have a web type behavior and a flange type behavior. And the main idea that we did this is because we wanted to study the lateral bracing system for the Lotte Tower. That was the main idea of this study. In general, it's very important for you to know what you want to extract from the optimization. In general, what it can do for you is to inform your intuition. That's one of the main things it does for you. And we also study other types of diagrid type solution. This was for a torsional load that is very much expected. And now I want to talk about the connection with topology optimization and additive manufacturing. And then this is the density-based formulation that we talked about. In general, we apply a filter, a convolution to the densities, and then I can have a volume constraint, other constraints, bounding constraints, and then this is the SIMP model, okay? Here I am using what is called nested formulation, okay? And all that this means is that the nesting means that equilibrium is being satisfied. And I can work either with a linear problem like here, or a nonlinear problem where I would minimize the residual of the problem. And then here, what happened is we developed some operators that could help us to get good solutions for the additive manufacturing problem. And here is just an illustration of the convolution operation of the density field. And here is a design domain where we fixed, here we put a load here. And now let's see, we have a volume fraction of 10%. And let's see what we are going to get. And then you can see the evolution of the problem, and this is using a density-based solution, and that's the one that you get. Okay, it's exactly the one that you get. So here, so far, so good. But in general, you don't get things that are that nice. And I am going to illustrate this to you. So we also solved this problem using the ground structure method. And then we got this solution here in white, as you can see. And I'll pass this around. You can see exactly the same problem, and two different techniques, but then we get two different solutions. Okay? And please, this is not a compliant mechanism. This is clamped here. Don't apply this force when I pass this around, okay? All right. So another problem here, just to indicate to you some of the problems that can happen. Take a look here. You can see the evolution of the topology, and I think just looking at the evolution of the problem can give you a lot of insight in what is going on. But you can see here a problem, right? You don't want to print this. Look here, there is a necking here. And then you can see here the detail of the necking. Then we need to go and fix this. And essentially you can see here with the level set, you can choose, because this goes between 0 and 1, this is 0.5, but no matter what you choose, you are always going to get this necking. And then what we did here, again, is to develop another operator related to the convolution operation that we can apply, and then you can see we can fix that problem. Okay? Now is the fixed problem, and this is the final example is a bridge problem, okay, as you can see, and this looks good, but if you look closely, this is very bad. You don't want to print this. This is not a bridge. Look at this. You get all disconnected things, holes, and so on. You need to fix this. And what we did here essentially was to employ a continuation in the SIMP model. That's the other operator that we developed. And now if we do this, take a look on the evolution of the problem. And then you will see that the penalization, there is a continuation here on the penalization of the SIMP. And this seems to give you a very beautiful solution in a tree-type structure. In general, topology optimization gives you very organic type of structures, okay? And this is the bridge. Actually, with this one, you can see things that you don't see over there. For example, there is a curvature here. When you touch it, you can see. And you can see how the trees change. At the top, there is only one tree, and then as we go, I have two. It's very interesting. I'll pass this around. You take a look. All right. And finally, what I would like to say is that I created a class at Illinois, and I also taught it at Georgia Tech. And essentially, we did a code that is called top slicer that allow us to essentially apply all these operators and get very good solutions that can be printed. And I did a homework. The final homework was a rapid prototyping for structural engineering. So each student could choose the structure that they like. For some reason, many of them chose bridges, for example. This chose the Eiffel Tower. There were about 50 students in the class, and these were groups of 2 or 3 students, and these are the designs that they did. And I think they enjoyed this kind of exercise. And these ideas are in a paper that will come up in structural and multidisciplinary optimization. In conclusion, I would like to say that maybe you have seen that body-centric finite elements, they provide a stable formulation for topology optimization, so that we can do stable topology optimization. And the topology optimization can be a very nice linkage between medicine and engineering, and also between architecture and engineering. And finally, there is a lot of room for contributions on the connection between topology optimization and additive manufacturing, especially regarding 4D printing. And if you want to talk more about 4D printing, I'll be glad to talk to you. Thank you very much.
So you about the material structure, I mean, you're right that it has the checkerboard type of effects, and usually you increase the filtering that also helps to reduce that, or if you kind of modify the meshes to do that. I'm kind of curious about the polygon elements that you introduced there, that seems to be, kind of reduces, the checkerboard effects of that. The polygon effect, do you need to do any types of refining of those polygon meshes, or
No.
how do you know what is the optimum mesh refinement in order to reduce that checkerboard effect?
Yeah, it's a very good question. Essentially, what happened is the polygonal formulation is naturally stable. Whenever you have a mixed variational problem, okay, you are going to get a stable solution. It may be inaccurate, it may not be accurate, but it will be stable. And then to address the accuracy, then we would need to do the conventional studies related to convergence and so on, mesh refinement, so that we can get the desirable level of accuracy. But for mixed variational problems, the formulation is stable. The Babuska-Bretzi condition that I showed, that's a necessary condition. That's the one that we investigated, but recently the people at the Franco-Bretzi's group, they proved the sufficiency condition for the polygonal discretizations. Okay.
I see.
Thank you for your talk. So,
Welcome.
a four-node element is also a polygonal element.
You are right.
Philosophically, right?
But very poor, like Mr. Square in the flat land, right? Very poor.
But my question is the difference in the performance of the polygonal element more because of the watch press function, the basis function?
No.
Or is it has no?
Excellent question, excellent question. His question, just so that everybody knows, he pointed out the triangles and quads, they are also polygonal. And he wanted to know if about the influence of the shape functions, and this is the good performances related to the watch press. No. In general, you can use other types of shape functions, and they work quite well. What happened is that in 2D we can do a very good job. There are many shape functions that are available, and people are using this especially in the computer graphics field. However, in 3D, I didn't talk about 3D, the story is not so nice, because there are lots of problems in the development of the shape functions. And for example, if the element is not strictly convex, for example, then some of the ideas that exist, they don't work, you know. And there are some ideas in the literature I can refer to you related to, for example, star convexity. Star convexity is a compromise in the sense that, for example, the centroid, the element may be non-convex. However, the centroid of the element is still inside the element, is not outside.
Just a quick follow-up. So is a four-node watch press equivalent to a quad linear?
Completely equivalent. Yes, yes, completely equivalent. Welcome.
Yeah, I just have a quick question. On the end of your presentation, when you showed some additive manufacturing techniques, I was just curious about, so you define a set of loading conditions and support conditions for your structure, and how does it evolve to know where to add material to grow? What's the mechanism underlying?
For example, maybe could I explain that with the bridge problem, for example?
Yeah.
Is that okay? Let's take a look there then. All right. Yeah, I think this will be very informative. I was very concerned about the time, so many things I did not explain. So what happened is this. The bridge here, this is the design domain, okay? This part here is a passive region. I am not going to touch it because I need this to apply the load. So this is a passive region, and this makes sense. This is the deck of the bridge. I don't want to change that. And then also these are the regions where I am going to apply the displacement boundary conditions, okay? And this is my volume fraction. Essentially, what I am doing here, okay, is minimizing the compliance. What happened is I am going to find the structure of a maximum stiffness that satisfies, I only have one constraint here that satisfies this volume constraint. At the end, the amount of material that will be in the bridge will be 10% of this entire domain. And then this is a gradient-based optimization that we have used. And then this here that you have seen is what gives you the evolution of the gradient-based algorithm. Okay, so then essentially I am doing many nonlinear iterations. Okay, and in each iteration I am solving both the boundary value problem and the optimizer. I am finding the gradients and looking for the sensitivities, following the gradients, and repeating the cycle. Okay.
Can I ask you a follow-up?
Yes.
Because this and also two of the models that you're passing around, the red and the white one over there, did I understand? The question is, like, for a given set of constraints like you've shown here, is there one optimal solution? I mean, I understand the different techniques.
Greg, I love your question.
But should we expect, like the Mitchell truss, we know about the Mitchell truss, is that the optimal? And well, just that, is there just one optimal?
Essentially, to be strict to address your answer for any of these solutions that I had here, all that I can guarantee is local optimum, and can never have any guarantee of any absolute optimum, except for the LP problem. In the ground structure, the LP, the objective is linear, the constraints are linear, therefore if the objective and the constraints are linear, then the solution is the global optimum. But in these ones, the problems are terribly nonlinear. However, what happened, Greg, is that we have some techniques that allow us, for example, like a continuation technique, is that the problem has lots of mountains and valleys, but then, for example, there is some bound, and I know that the optimal solution is around here. And then we have this continuation technique that will move us around that direction, and I know the optimal point is this, but I may be getting this, I may be getting that, I do not know. But also I would not mind, because once I am in that neighborhood, I am quite satisfied. And then if we compute, for example, the objective, the stiffness, and the evolution of the problem, for example, then we can see that we are really converging, and then we are satisfied with that. Yeah, but these problems are terribly nonlinear.
Ask a question.
Yes.
Does the material that you choose at the very beginning affects the optimized solution? For example, if you choose elastic material, or you choose elastoplastic material,
Correct.
does that affect?
Oh, tremendous effect. All the solutions that I have shown here, the constitutive model has been linear, and most of the solutions in the literature, they are linear. Recently we did some nonlinear analysis with hyperelastic trusses, and this has been published in Structural and Multidisciplinary Optimization. This is available on my website. There are many issues there that I decided not to address here. Maybe if I come back here, then I can give a talk on nonlinear state topology optimization. And the final part of your question is regarding the elastoplastic model. What happened is, with the hyperelastic, there is no energy dissipation. Then we have an elastoplastic model, there will be energy dissipation, and then of course there are formulations and there are proposals in the literature to address those, but there are some issues that essentially are associated to the fact that during the evolution process you have a dissipative process, and then there are some issues there. Okay. One approach that we are, one of my students, he's working on this right now, is that if you have an elastoplastic constitutive model, because I want to see if what is in the literature is really consistent, then what we are doing, we are using a limit type analysis that is hyperelastic, but we guarantee that in the limit the two formulations converge. But then after I do that, I will feel comfortable, because in my formulation it is hyperelastic, there will be no energy dissipation. But we are doing both formulations to try to understand it better.
In this problem you gave the volume as an initial constraint, but shouldn't topology optimization also incorporate optimization of volume by?
Oh yes, yes. Yes, and you can choose. For example, you can flip them. Here I maximize the stiffness with a volume constraint, right? And another idea that you can do, you can minimize the volume or minimize the weight with a stiffness constraint, for example, or other types of constraints. Absolutely, yeah. And actually for a linear state problem, we can show that there is some equivalence between the two formulations. And that proof is given in the book by Clarbring and Christensen. That's a very good point. And sometimes one formulation may be preferred over the other, depending on your objective, on what you want. For example, sometimes weight may be the thing that you really want to control, or sometimes maybe the stiffness. And then one formulation may be preferred over the other one. I have many questions.
Very interesting presentation, Professor.
Thank you.
Let me ask a question as a practicing engineer. When I look at this structure and imagine trying to build something like that out of steel, out of aluminum, something that would be for civil engineering application, I imagine tremendous problems, A, with the connection.
Oh, yes.
And then B, finding a way to demonstrate that it is somehow compliant with current codes and practice.
Absolutely.
Would you care to comment on your vision of how long it would take for these kinds of issues to get worked out to the point where these techniques could be used in real civil engineering structures?
I love your question, and I am thinking here on how to approach the answer. Do we really, let me ask you a question back. Do we really want to implement these topology optimizations directly into a code?
Sorry.
Do we really want to implement a solution that I get from topology optimization directly in a code to go and build it? That's one you do?
You can't build it otherwise.
Well,
Codes have to change, perhaps.
or we could change too. What I am trying to motivate here is the following. The way that I see is maybe, and again, this is my personal view, okay? And especially in this interaction that we had with SOM, the way that I see the topology optimization is not the way that this would replace the engineer and the architect. The way I see is that this can inform your intuition. This can provide you insight that you would never get otherwise. And that's the way that I see the value of these techniques. For example, I talk to the students today in the class that I teach. In general, we think that if I have a beam and I put more material, I get a stiffer solution, right? And I give a homework to the students addressing load path, okay? So that when you do design, you want to make sure that the loads go where you want them to go, not where they want to go. And then I give them a problem where the stiffest solution is the lightest, okay? But you control the load path. And then these are the kind of ideas that I think that topology optimization can be wonderful, is to inform our intuition, to help you as a designer to do a better design, to do some unique things, to explore new forms, to explore new ideas, to play with strange types of objectives that you may have and constraints. And then that can essentially also help in the dialogue between engineers and architects. But this is my personal view. And there is another view that is related to what you asked, is that some people believe that if this is to be useful, that we need to reach a stage where this is automated enough that we can reach the stage that you can get a design that is that can be manufactured directly, okay, or with minimal changes, and that is possible. But my experience, my work has been more in the sense that I indicated to you that we want to use this to inform our engineering and architecture intuition.
Marty, if I could just make a comment on that too. A pitch that, I think in some of the tall buildings going up in San Francisco now, they're not defined by any systems that are in the building code, but they're really permitted by the city by demonstrating using methods of nonlinear analysis, seismic hazard analysis, so which kind of frees you up from the traditional constraints of building codes. And I think to achieve some of these things here, it requires that too. In other words, there are no classical beams or columns in there, so which chapter of AISC do you go to?
Yes.
But I would kind of hope that, maybe we couple this with sort of advances in, a lot of the work we've been doing here on risk assessment and things like that could, that's sort of enabling the design check after we've kind of achieved some topology that we want. That topologies that might not be recognized by traditional building codes.
Yes. Lots of questions. I don't know who is next.
This method you're using, do they take into account the self-weight of the material as it's being built or as it's being removed? Once that goes into the equation, or material itself, the structure itself, part of the equation is mass and its weight?
It's a very good point. Essentially, what the only consideration in all the formulations we had here was the volume, okay? Because in general, the volume will correlate with the weight, but a better idea probably is what you are describing, to take care of the weight directly. And this also will introduce some other issues in the formulation, like, for example, design-dependent loads and so on. But in everything I showed here, we were controlling the volume as the variable.
So the structure itself now is mass, means you started with certain uniform pressure on that bridge. That's the only load that all these elements are carrying. They're not carrying the whole load.
Correct. Yes. What I want to motivate to you, this is an excellent question, but what I want to motivate is the following. When you have the weight, then you have a design-dependent loading, okay? It's a design-dependent, because the distribution is changing as the design changes. And these techniques that I showed here will not apply. They have to be modified.
Next student.
Yes.
So the ground structure method and the density method sometimes gives different solutions. So how do you decide which method to use in which case and which one actually gives the best solution?
I don't know. But what happened, as you pointed out, they give you different solutions, okay? And which one is right or not, I do not know, because essentially that will depend on what you want to achieve, okay? What you want to achieve, okay? And sometimes a density-based formulation may be better, and sometimes a ground structure formulation may be better. For example, in general, what we found out, we have done this study for buildings with density-based methods, but density-based methods, we have very hard time to get a very high density of members that are discrete, that are well-defined. But with the ground structure, that happens naturally, and that resembles a diagrid type solution that is very much useful in design. And then for this, I would say the ground structure probably would be the preferred method. Okay. In one instance, there is no silver bullet or no perfect method. In some instances, one method may be preferable. In other instances, the other method may be preferable. Yes.
Do you have a concern that highly optimizing a structure to a particular loading case might make it susceptible to a different kind of loading case?
Very good point. Yes. Yes. He is asking that we are optimizing the structure here for one load case, right? This was only for bending. For one load case, real structures have hundreds of load cases, right? So, optimizing it for one load case will make it good for other load cases? No, of course not. No, it's not going to do that. And then you say, why don't we put all the load cases? Essentially, we may not want to do that. What we find out is that when you put too many load cases, you get a complete dense structure with all your members there. Essentially, you are not getting anything useful. And again, I go back, and again, this is my professional bias. I go back to the answer that I gave to him. The way I see topology optimization is a means to inform your intuition so that you can do better engineering, better architecture, a better design, but not to replace your job as an engineer or a designer. Although in the future that may happen, but that's the way that I see how the technique is most useful. And now what we are doing, one of my students, her PhD, Shelley, she's using stochastic sampling to do topology optimization for many load cases, for hundreds of load cases, for example, because in some instances we may be interested on that. And what is interesting here is that we are using a stochastic technique to solve a deterministic problem. But what happens is if you have 100 load cases, just think about it, one formulation, just we here are essentially we are minimizing the compliance, right, the energy, and then you would have one for each load case. And then if you treat all of them, that can be very expensive, okay? And with the stochastic sampling, instead of treating, for example, a few hundred or 1,000 load cases, we could get almost the same results with 5 or 10 load cases. Let's say you have 200, and then I do 10 with the stochastic sampling, and the results may be similar. This is some ongoing work. Yeah, very good question.
Maybe let's get some new people. And one professor, and then we'll go back to the students.
Thank you for this very nice presentation. My question is also with regard to the material you use for your computations. You mentioned that the material highly influences the behavior.
Correct.
But then you said you use linear elastic materials for these.
Correct.
But you had one example where you had a piezoelectric material.
Correct.
How do you account for that? Is the compliance accounting for effects?
But that one was, I didn't show the formulation. That one was a linear formulation, but a coupled formulation, a piezoelectric formulation with mechanical and electrical components on your stiffness matrix. And that was a different formulation from what I showed here. I didn't talk about that.
But do you take into account the electric effects for that optimization problem?
Yeah, but it's piezoelectric, and it was linear too. But
the compliance term, you have to add functions to the compliance.
Yeah, but the optimization, the objective, that one was not compliance. That one was we define a term that is called electromechanical conversion term that deals with the piezoelectric terms, that kappa, and that's the one we wanted to maximize. There is no compliance there. Okay. Make sense?
Yeah, makes sense.
All right.
So I just had one quick question that the organic shapes may not be very practical or they might be expensive to construct.
Correct.
So how can we incorporate such constraints that which make your optimized shape easy to construct? It makes it constructible.
Yeah. Let me give you an answer in two parts. The first part, I would answer to you exactly what I answered to him. And the second part, I will answer what probably you are mostly looking for. The major criticism of topology optimization in the literature is what you are saying, and also that he asked. You do all these calculations, and they are not very easy to do. And at the end, how do you do these things? How do you manufacture them? How will you translate this from the theory to something that can be engineered, right? One idea now, especially with additive manufacturing that is coming up, is that what happens is you can work with manufacturing constraints. And then you can drive the optimization. For example, maybe you want to put some limit on the member size. Maybe you want to impose symmetry. For example, if you do topology optimization, even the simple, I didn't talk about that, but even the simplest formulations, if you use the standard formulations that are in the literature, and I have one educational part of my site, I just illustrate it to you, you never get anything useful for a civil engineer. And then, for example, you can do constraints associated with symmetry, with pattern gradation, for example, maybe buildings, for example, you want the topology to change between floors and not to have a floor in the middle of a change of topology, for example. And you want to put other types of manufacturing constraints and then change your topology optimization to add those constraints. But you need to be careful because if you keep doing what I just said, you may end up in a situation that you may have no feasible domain. Then you have to really be careful with what you are looking for and the kind of constraints that you can add in the formulation so that you can get a useful result. And manufacturing constraints is a big area of research. There are lots of things going on into that. And with additive manufacturing, I think that area will be developed a lot because we are getting in a stage more and more where things can be done. And if you allow me, maybe just one more comment. What happened is actually topology optimization has been quite well developed for mechanical engineering and aerospace. For example, Airbus, the A380, when they designed the wing, that was done with topology optimization. And I don't quite remember, but I think they saved about 500 kilograms or so total or per wing, okay, for the Airbus A380 by using topology optimization. And then many automobiles, for example, Toyota, I have a friend, Professor Noboru Kikuchi. I mean, he is now the worldwide head of the Toyota R&D. He used to be the head of Toyota R&D in the US, and now he's head of the worldwide division. He wrote the first paper in topology optimization in 1988, the computational approach with Benson, okay? And then this has been very developed in other fields. And what I wanted to show you here are some of the techniques that we are trying to develop to tailor topology optimization to structures like buildings and bridges that are of interest to the civil engineer. Because as I said, if you are curious, look on my website, the educational part. If you use the standard technique to do things like this, you get completely useless results.
I think we're actually, well, it's getting late, so I think Glaucio, we can hang around here to handle other folks' questions, but I think we'll maybe end our formal part here. Kind of, to me, this is like just amazing. It looks like about 3 lifetimes worth of work.
Thanks, Greg.
At least my lifetime. But, and as I mentioned, Glaucio has new work coming out on foldable structures, so I would encourage you to, if you're curious about these things, take a look at his website. He gave us a lot of reading by assignments today, by the way. So I'd really like to give our gratitude for you coming out here, for all the work you're doing, and for kind of sharing that today, and for everybody here who came out. So.
Thank you very much. Thanks for inviting me. Thank you. Thank you. Thank you. Thank you very much.